Hi everyone. In this example, we're going to factor this fifth-degree polynomial over the reals, r, and find all of its real zeros. And then we're going to factor this polynomial over c and find all of its complex zeros. Okay, so first off, when we factor this, what is the first thing we factor out? We normally try to factor out its GCF first. What is the GCF? Here, the GCF is x. Notice that if there is no non-zero constant term here, then x is probably a factor. So the GCF is x. We factor it out. When we factor, we divide. We factor out the x, and then notice that each of the exponents goes down by 1. In yet another factor, we get x to the fourth plus x to the second minus 6. Now here, we have a fourth-degree polynomial. And you might be afraid. You might wonder, are we stuck? But we're not, because this fourth-degree polynomial is in what form? It is in quadratic form. And why is that? Because when we try the substitution, u equals x squared, the middle power of x, we end up with a QD, a quadratic trinomial. Notice that the leading exponent, the 4 here, is twice this exponent, the 2. And then negative 6 is a constant term. So when you apply this substitution, we end up with x times the quantity u squared plus u minus 6. And we factor this QD in u. So when we do that, we have, don't forget the x, and then we have the factor u plus 3, and then the factor u minus 2, or vice versa. Don't forget, we have to go back to x. U is x squared. Let's go back. We have x, don't forget, the factor x squared plus 3, and the factor x squared minus 2. Now, you didn't have to do the substitution. You could have gone directly from here to here. Remember that you have x squareds here and not x's. But you could have gone directly from here to here without going through the substitution, although the substitution does help many students. Now, at this point, we have factored this completely over z, the set of integers, or for that matter, q, the set of rational numbers. We factored over z, the set of integers, or q, the set of rational numbers. All right, but if we wanted to factor this over the reals, and that was the instruction here for us to factor over the reals, what else could we factor? Well, the x is just a nice linear. It's just an x. Over here, x squared plus 3. Well, here's a hint. Here's a hint. Now, this is for quadratic specifically. A quadratic can be factored over the reals, the set of real numbers, if and only if it has real zeros. That's true for quadratics. Well, x squared plus 3, does that have any real zeros? The answer is no. And by the way, we're appealing to the factor theorem here. If k were a real zero, then x minus k would be a factor. But now what about x squared minus 2? Well, x squared minus 2 does have real zeros. And you can think of this, in fact, as a difference of two squares. Maybe not nice squares necessarily, but the difference of two squares. How could you factor x squared minus 2? you can factor it as the factor x plus root 2 and the factor x minus root 2. 2 is the square of the square root of 2. And at this point, we have completely factored the fifth degree polynomial over the reals. Now from these factors, we are able to get the real zeros. What are the real values of x that will make this equal to 0, this equal to 0, and this equal to 0? Well, x equals 0 makes this factor 0. Negative root 2 makes this factor equal to 0, and positive root 2, when plugged in for x, makes this factor equal to 0. And we have no real zeros coming from here. Notice this quadratic, x squared plus 3, is quadratic, and it's prime or irreducible over the reals. X squared plus 3 is a quadratic that is prime or irreducible over the reals. All right. So we have the three real zeros here at x equals 0, negative root 2, and positive root 2. Now notice that each of these has multiplicity 1 on the factors. And remember, these real zeros correspond to what points on the graph of y equals this fifth degree. Remember that the real zeros of the function correspond to the x-intercepts of the graph. So if we're to graph this thing, y equals this fifth degree, what would it look like? I'll give you 15 seconds. Sketch a graph. All right, folks. Remember, these correspond to x-intercepts over here, the zeros, 0, and plus or minus root 2. All right, so let's graph this thing. Y equals x to the fifth plus x to the third minus 6x. Okay. Because the leading term is x to the fifth, we have a rising stake in the long run. And because the factorization looks like this, okay, again, we have x-intercepts at 0, 0, at negative square root of 2, 0, which is a negative square root of 2 is about negative 1.4, and positive square root of 2, 0. And notice that at each of these x-intercepts, the graph will cut. Cut like a snake, cut like a snake, cut like a snake. And that's because the multiplicities on these factors are odd. They're ones. And we're not going to discuss the x squared plus 3 right now. Notice something else. What kind of function is this? Where f of x equals x to the fifth plus x to the third minus 6x to the first. We have here an odd function, which means that the graph is going to be symmetric about the what? About the origin, 0, 0. Notice that the origin is a point on the graph. It has to be for any odd function where 0 is in the domain. And notice that we do have symmetry about the origin. If we were to take the snake, rotate it 180 degrees about the origin, we get the same snake. Odd function, symmetry about the origin. So we know a lot about the graph of this thing. Now, What are a couple of points that we cannot locate just yet? We're going to need calculus. Well, we're going to need calculus for the local max point over here and the local min point over here, the turning points. In calculus, you're going to set the derivative equal to 0, solve for x, and that will help you find the turning points here. All right, so just from the factorization over the reals, we can basically graph this thing very well. Next, we're going to talk about the factorization over C, the set of complex numbers, and some patterns.